We've built artificial intelligence capable of reasoning through quantum physics and writing symphonies. Yet ask that same AI to fetch a private file or update a spreadsheet, and the system hits a wall. Giving these models direct access to the outside world is notoriously risky, often exposing the entire network to immediate vulnerabilities. To get around this, developers have spent years building custom bridges. If you wanted your AI assistant to read your GitHub repository, you had to write a specific hard-coded adapter just for GitHub. If you wanted it to query your local database, you built another custom adapter from scratch. A single AI model trying to talk to dozens of external tools creates a fragile, tangled web of conflicting API connections. Every time a service updates, the adapter breaks, creating a massive maintenance bottleneck. For all its processing power, the AI was effectively a brain trapped in a jar. It was highly capable of thought, but completely isolated from real-world execution. That isolation is exactly what Anthropic's Model Context Protocol, or MCP, is designed to solve. MCP is an open standard that functions as a universal adapter for artificial intelligence. MCP replaces dozens of custom adapters with a unified two-way communication channel. Models and tools neatly plug into it. Because it's standardized, AI automatically scans and learns available tools in real time without hard-coded instructions. This creates an interoperable ecosystem where any model can talk to any tool. A model from OpenAI or Google can use the exact same enterprise connections as an Anthropic model because the AI's logic is no longer tied to the specific tool it uses. This architectural blueprint illustrates exactly how MCP achieves that interoperability through a three-part system. On the far left, we have the host. This is the user-facing AI application, like your coding interface or chat window, where you actually type your prompt and initiate a workflow. Operating quietly inside that host is the client. Think of the client as the internal translator. Its sole job is to maintain a strict one-to-one communication link, taking the user's messy request and structuring it into a standardized format. On the other end of that bridge is the server. The MCP server is a completely independent program, interfacing directly with your external tools, local files, and web APIs. It manages the actual execution of tasks outside the AI environment. When a user asks a question, the host analyzes the intent and hands the request to the client. The client then queries the server. Finally, the server executes the external API call, retrieves the data, and sends the packaged result back to the AI. Because the execution happens entirely on the server, a software developer only has to write an MCP server once. The moment it goes live, any AI model equipped with an MCP client can plug in and use it. To make this practical, an MCP server offers three specific capabilities. The first is tools. Tools allow the AI model to actively invoke external operations. This is what lets an AI ping a server to fetch the latest stock prices, or send an automated message to a Slack channel. The second capability is resources. While tools are for taking action, resources are for reading data. They grant the AI passive access to structured information, allowing the model to read a massive local text file or pull tables from a company database without altering the original files. The third capability is prompts. These are reusable workflow templates maintained by the server itself. They help standardize complex, repetitive tasks, so the AI knows exactly how to format a customer support email or summarize a financial report. When you combine these three capabilities, the real-world applications become highly advanced. A software engineer can use an MCP-enabled code editor to instantly read thousands of files in a local directory using resources, and then autonomously draft and test a brand new feature using tools. These capabilities allow AI to perform actual labor in professional workflows, moving beyond simple chat and directly integrating with the software environments humans use daily. But connecting an intelligent agent to an array of external services introduces a severe vulnerability. The moment you give an AI dynamic access to outside databases and file systems, you dismantle traditional software security perimeters. The protocol itself is solely designed for structured data exchange. It verifies data types and routes requests, but it entirely lacks built-in mechanisms for runtime isolation or privilege control. The security boundaries of an MCP server depend entirely on the machine hosting it. Looking at our architectural diagram, If an MCP server has high privileges, an attacker can feed the AI a malicious prompt. This creates a sandbox escape. The corrupted instruction bypasses the client's checks and tricks the server into executing commands outside its designated container. The stakes here are incredibly high. Even in a perfectly functioning network, a hijacked AI could be manipulated into quietly deleting local system files or exfiltrating private company data, completely hidden from the user's view. To prevent these breaches, developers have to enforce their own strict trust boundaries. Since the protocol won't do it for them, administrators must build explicit, limited permission controls directly into the server software, ensuring it only has access to exactly what it needs to function. Teams also have to deploy continuous auditing and real-time monitoring across the communication link. You have to catch anomalous behavior, like a sudden request to wipe a database, and block it before the server executes the command. Despite the necessary caution, the value proposition of MCP remains clear. It resolves the bottleneck of API fragmentation, standardizing how artificial intelligence accesses and interacts with external data and tools. We have successfully given these models the ability to interact with the world around them. Now, to make autonomous agents viable, we must implement the granular security controls necessary to protect the expansive connectivity MCP enables.